Welcome to the Introduction to Operating Systems class. Let's get started with Chapter 1. So what is an operating system? It's the program that manages the computer hardware. It allows applications to run and makes it easier for the user to interact with the system. We can consider a computer system to be divided into four main components. There's the hardware, the operating system that manages the hardware and allows interaction with the hardware. There are application programs. And finally, there are users. These users could be people or they could be other computers connecting to transfer data or remotely execute code. Here we see the four main components: the users, the applications, the operating system, and the hardware. There are various types of users. We can consider, for example, a normal PC user. One person using the computer at a time, but they may be running multiple programs. We may have terminal users connected to a remote machine, and that machine may have many users at once. We may have a workstation user, which might be somewhere between the previous two, where you're executing some local programs and also accessing shared resources remotely. You may have handheld users, which are similar to PC users, but the machine itself is smaller, it has a simpler interface, and it has other concerns, such as a consideration for battery life. One way to look at an operating system is that it is a resource allocator. It manages all the system's resources, and when there are conflicting requests for the resources, it has to decide which program or which user gets to use them first. The operating system is also a control program. It controls the execution of programs to prevent errors and improper use of the computer. One can also think of the operating system as being like a government. It doesn't do productive work, but it provides an environment in which productive work can occur. There really is no universally accepted definition of exactly what an operating system is. One approximation is everything the vendor ships when you order the operating system, but that can vary quite a bit between one operating system and one vendor and another. The key core part of the operating system, the one program that runs at all times on the computer, is what we call the kernel. Everything else is either a system program that ships with the operating system but isn't part of the kernel, or it's an application. Two key attributes of operating systems are efficiency and convenience. Usually there's some sort of compromise between the two. It's important to remember that RAM main memory contents are volatile. They're lost when the machine is turned off. The first program that's run, the Bootstrap program, must be stored in non-volatile memory. The Bootstrap program loads the operating system kernel from non-volatile storage, such as a hard drive or a solid-state drive. What are some of the hardware components of a typical computer system? We have a CPU or CPUs, memory, and I/O devices that are connected by a bus or buses. The CPU and I/O devices frequently need to read or write memory for data, and in the CPU case, for instructions. Input and output devices are generally accessed through some sort of device controller, such as a USB controller, disk drive controller, SCSI controller, and so on. Interrupts are normally used to coordinate transfers of data. The I/O device controller sends a hardware signal or interrupt request to the processor to let it know when data have been transferred, or, for example, when an error occurs. What happens when an interrupt occurs? Most processors have a priority system in place. Assuming this interrupt is of high enough priority to be enabled, its interrupt number is used to look up in a table to find the address of the service routine. The system has to save the return address, in other words, the address of the instruction that was executing when the interrupt occurred, and the processor's state, including the registers. It then turns off other interrupts, or at least those of lower priority, and then the interrupt handler or service routine runs. Operating systems are generally interrupt driven in the sense that most events occur in response to hardware or software interrupts. Here's an example of input and output processing occurring in response to interrupts. A program running on the CPU requests I/O via traps or software interrupts used for system calls. The I/O device controller tells the CPU that its request is completed via a hardware interrupt. Each I/O device interface has certain registers that are used to control and configure it, as well as transfer data. The program that directly interacts with the device interface is called a device driver or device controller program. This program loads the appropriate registers to configure the device for the transfer. The CPU executes the instructions of the device driver, which read or write the data from the device interface and put it in or read it from memory, one access per transfer. DMA, or direct memory access, can streamline this. It takes the CPU out as the middleman. This is useful for large block transfers. There are multiple types of storage in a typical computer system. No one type of storage is superior in all ways. Some are faster and some are slower. Some are more or less expensive. Some technologies require more or less power. Some are volatile and some are non-volatile, and so forth. Main memory is directly addressable by the CPU. Secondary memory, such as disks, is treated like an I/O device. Storage on most, nearly all, computers is arranged hierarchically. Fast memory is expensive and usually volatile. Cheap memory is usually slow and may or may not be volatile. For example, dynamic RAM is volatile, but disks and solid-state drives are not. The idea of caching is that we try to keep the frequently used items as far up the hierarchy as possible for faster access. Here we see a pictorial representation of the storage hierarchy that's in typical computer systems. The higher levels are fast and expensive storage, so we have less of it. The lower layers are slower and cheaper, but we have more of it. Here we see that the higher layers are volatile memory and the lower layers are made of non-volatile memory. The operating system wants to make the whole thing work together as seamlessly as possible. Caching is an important principle in computer systems and happens at different levels in the computer. The basic idea is that information that we're using frequently is going to be temporarily copied from slower storage to faster storage so we can access it more quickly. When an item is referenced, we check the cache or the faster level of storage first to see if the information we need is there. If it is, we use the information directly from that level and we don't have to go to the slower memory in order to find it. If not, we go to the slower memory, we copy it to the cache, and from now on we'll use it from there. Now, of course, the cache is always smaller than the level of storage that's being cached. Cache management is important. We have to be able to keep the right information in the faster memory, and we have to be able to replace it when necessary, since the cache is of limited size. Many, but no longer necessarily most, computer systems have a single processor. Now, dual and quad-core processors are very common. These are multiprocessors on a chip, multiple independent CPUs that may share cache and do share access to the same memory system and I/O. There are two types of multiprocessing. Asymmetric multiprocessing, where each CPU has a different role. For example, one may handle I/O while others don't. Or symmetric multiprocessing, where all CPUs are essentially created equal. In a system, each CPU behaves as shown in this model. In a multiprocessor, the CPUs could be on separate chips or all on the same multi-core chip. In either case, they share access to memory. In a symmetric multiprocessor, each processor can perform any task, whether it's operating system or application. Here we see a dual-core chip where two complete CPU cores and the associated cache are fabricated on one semiconductor chip. Systems with 4 or more cores are becoming increasingly popular. Another type of parallel system is a cluster or multi-computer, which consists of multiple complete separate computers that are connected together. Because of this, they don't all have to run the same operating system as multiprocessors do. They may share secondary storage, but they don't share cache or main memory. This type of system has high availability and scalability because the types of interconnection networks that are used usually allow more nodes to be added relatively easily. Dedicating a system to only one job at a time is not very efficient use of hardware. Instead, we do multi-programming, where we keep multiple jobs in memory at all times so the CPU always has something to do. When one job has to wait, for example on an input or output operation, the operating system will switch to run another job. Time sharing, or multitasking, is the same concept as multi-programming, but task switches occur more frequently, so each job can be interactive with the user. In other words, we're looking for a short response time. Virtual memory can be used. It gives each process or job the illusion that it owns the entire memory space of the system, even though it doesn't. In fact, multiple jobs are loaded at once, as we'll see in the next slide. Here we see multiple jobs, or processes, and the operating system itself, all loaded into memory at once. A process is a program that is loaded into memory and running, as opposed to only residing on the disk but not currently active. Others may reside in a job pool on disk and get loaded in when space is available, based on a job scheduling algorithm. The decision of what to run next of those jobs that do reside in memory is up to the CPU scheduling algorithm. In most operating systems, most system activity is in response to interrupts and traps, or exceptions in general. Generally, there is a special interrupt that occurs periodically to avoid infinite loops. A watchdog timer to keep the system from hanging up is especially important in embedded systems. Modern CPUs support at least two modes of operation in order to allow for secure operation of the system. User mode is for running application programs, and there's also a supervisor mode, also known as system mode, privileged mode, or kernel mode. A special bit in a system register determines the current mode, and changing that bit is a privileged operation. The mode bit must be in the proper state to execute privileged instructions. The system boots up in supervisor mode, and exceptions are also handled in supervisor mode. Again, a process is a program that has been loaded into memory and is in some stage of execution. As we'll see later in chapters 3 and 4, processes can be single or multi-threaded. In a given system, many processes can exist at one time. In a single CPU system, only one process is actually running at a time. In a multiprocessor system, multiple processes can run at the same time in parallel. Here are some of the things that the operating system needs to be able to do with respect to processes. It needs to be able to create and delete them, suspend them from running and resume them later. It needs to provide mechanisms for synchronization between processes and communication between processes. And it also needs to provide mechanisms for deadlock handling. In other words, if multiple processes are waiting on something, we don't want process A waiting on process B waiting on process C, which is waiting on process A. In other words, we want to avoid mutual or cyclical blocking. Everything a process needs, in terms of code and data, needs to be in main memory for execution. We can't execute directly from secondary storage. Almost all modern computers have a hardware MMU, or Memory Management Unit, to assist in managing the mapping of a process's memory space into physical main memory. We need file storage for code and data to support normal computer system operations. We don't want each individual application to have to do this its own way. This would be inefficient and there would be no standards. We don't want applications concerned with the details of how files are actually stored on different types of devices. So what does the operating system need to do? It needs to be able to create and delete files and directories. It needs to provide primitives for manipulation of files and directories, map files onto the secondary storage medium, and periodically backup files onto some sort of stable or non-volatile storage medium. Main memory is too small and too volatile to hold everything we need all the time, so we need to keep a lot of our information in files on disk. These files are organized in folders or directories for ease of finding the needed information. The operating system must manage all this and enforce any restrictions there may be on access. Here we examine the characteristics of various levels of the storage hierarchy. Notice that both the size and the speed vary by orders of magnitude as you move from the top to the bottom. The compiler, or in some cases an assembly language programmer, chooses what values to move in and out of registers. The cache is managed by a hardware cache controller. Movement of information between main memory and the disk is controlled by the operating system with hardware support from the MMU. Over time, a given piece of data can move between different layers of the storage hierarchy. We need to be careful to always use the most recent value, no matter where it might currently be stored. In a multiprocessor environment, we have to worry about cache coherency such that all CPUs have the most recent value cached locally. Either that, or we would need to refrain from caching shared data that can be written to. Read-only data presents no problem. One purpose of the operating system is to abstract the details of I/O from application programs. We mentioned device drivers before. Typically there is a generic device driver interface, but the specific details of each device driver will be different depending on the characteristics of that particular device. If there is only one user and one program running at a time, then there's no problem with conflicting access to memory or other resources. But that is usually not the case, and so the operating system needs to provide protection, which is mechanisms that are used for controlling accesses by processes to resources. We will look at this in more detail later on in Chapter 14. Protection is more of low-level mechanisms, while security is more of a system-level function. We'll look at security later in Chapter 15. Operating systems are designed for a wide variety of computing environments, including, for example, PCs, whether desktop or laptop, workstations, and handheld devices such as tablets or phones. Perhaps the largest but invisible market segment is embedded computers, those that exist inside other devices such as TVs, video players, appliances, cars, printers, games, and so on. Their operating system requirements are different, and they may need to interact with the user in real time. Once upon a time, most computing environments were isolated, but now most computers are networked. Often there is a broadband external connection that's tied to the local network through some sort of wired or wireless router. One common type of computing environment is a client-server environment. Once upon a time, the clients were typically dumb terminals, but nowadays they're usually PCs or even handheld devices. In any case, the idea is that the bulk of the computational and/or storage capability is on the remote server rather than the local device. The clients are connected to the server by a network. This could be the internet, with or without a VPN or virtual private network, or it could possibly be an intranet within a local site. Another type of computing environment is peer-to-peer computing, where the word peer means equal, such as being judged by a jury of your peers. In other words, citizens that have the same rights and responsibilities as you. In a peer-to-peer network, each node, each computer in the system may be either a client or a server or both at the same time. You're probably familiar with some of the examples of peer-to-peer computing networks, and you may have used these or more recent examples yourself. Web-based computing has become very common. Nowadays, almost everyone has connectivity at home, work, school, or in a public library, whether it's on a PC, a tablet, or even cell phones. To support web-based computing, large websites may use load balancers to control traffic among their servers. PC operating systems that used to be client-side only have now evolved into newer operating systems that can allow the computer to be a client and a server. Operating systems can be open source or proprietary. The most common example of an open source operating system is Linux, which we will install and learn about in our lab projects. Linux was started in 1991 by Linus Torvalds and has grown into a massive set of projects, different distributions with different features and different target audiences. With proprietary operating systems, for example Windows, the manufacturer does not provide the source code to outside entities, like us, so it's harder to study it and we can't modify it to suit our needs. Generally, with open source operating systems, for example Linux, there's a large community of people working on improving the system. It can be easier to get help, and because there are more eyes on the code, this can mean fewer bugs and quicker fixes for bugs. This concludes our discussion of topics from Chapter 1.